Ever felt that blast of hot air from your fridge or air conditioner and wondered if there's a better way to keep things cool? A quieter way? A more environmentally friendly way? Well, buckle up, because today we're diving into a revolution in cooling technology that sounds straight out of science fiction, but is very much science fact: nano-engineered thermoelectrics. Imagine a world without bulky, noisy compressors hogging space and energy, or a world where the refrigerants cooling our homes and businesses aren't a threat to the planet. This isn't just a dream. Researchers are making incredible strides, and institutions like the Johns Hopkins Applied Physics Laboratory, or APL, along with industry giants like Samsung, are leading the charge. They've developed a new class of materials called chess that's controlled hierarchically engineered superlattice structures. Sounds complex, right? But the concept is elegantly powerful. We're talking about engineering materials at the nanoscale in super thin films to get them to do exactly what we want. So how does this magic work? It's all about meticulously controlling how these materials conduct heat and electricity. The goal is to make them terrible at letting heat pass through, that's low thermal conductivity, but fantastic at conducting electricity and generating voltage from temperature differences, which is called the Seebeck effect. Achieving this perfect balance boosts something called the thermoelectric figure of merit, or ZT. And these new nano-engineered materials? They're showing ZT values dramatically higher than anything we've seen before, especially at room temperature. These devices use what's known as the Peltier effect. Simply put, you pass an electric current through a junction of two special semiconductor materials, and one side gets cold while the other gets hot. It's solid-state heat pumping, meaning no moving parts like compressors. The benefits? Think whisper-quiet operation, incredible reliability, and much smaller, lighter cooling units. One of the most exciting aspects is scalability. The manufacturing techniques, like something called metal organic chemical vapor deposition, are already widely used for making things like solar cells and LEDs. This means we can potentially produce these advanced cooling materials on a large scale, cost-effectively. And get this. These thin film technologies use an incredibly small amount of active material per cooling unit, sometimes as little as a grain of sand. This drastically cuts down production costs. And could acquisitions bring this tech to the mass market? Researchers are reporting substantial boosts in cooling efficiency, not just with the materials themselves, but in actual integrated refrigeration systems. This isn't just lab bench theory, it's working in practical settings. The potential applications are huge. We're talking everything from smaller, more efficient portable fridges and better cooling for our ever-shrinking electronics, to revolutionizing building air conditioning and keeping massive data centers chilled. Think about how lithium-ion batteries scaled up from our phones to powering electric cars. That's the kind of adaptability we're looking at here, and it doesn't stop at cooling. These materials are so versatile, they could even be used for energy harvesting. Imagine your devices being powered by converting waste heat, maybe even from your own body, into electricity. With continued research, perhaps even integrating AI to make systems even smarter and more efficient, we're truly on the cusp of a cooling revolution. A fascinating glimpse into a cooler, cleaner future. Thanks for tuning in.